If you FOIL these, that's what? A and A is A, plus, what do we have? A, B bar, plus, what about this one? A, B, plus B, B bar. Trying to prove why the answer is A. What happens to B or B bar? B and B bar. That's a 0. That's an AND gate with one input 1, the other one is 0. It doesn't matter what B is. One is going to be 1, one is going to be 0. It's an AND gate with one input 0, that's a 0. Down here on the bottom, what do they have in common? A. If you take an A out, what's left? 1 plus B bar plus B. That's an OR gate with one of the input already 1. 1 ORed with anything is what? Better be 1. So that's why the answer is A. A plus B bar equals A. Those are important because a lot of times you want to go from what we call sum of product to product of sums. So let's talk about these. Sum of product, product of sum. Minterms and Maxterms, we call them. Okay. Sum of product. Let's talk about the word sum of product, product of sum. Sum, the term sum. When it says sum means what? So a sum term is one or more terms connected by OR. That's what it says here. So like A plus B bar plus C, that's a sum term. And those are called max terms. A standard sum term, also called max terms. A product, let's look at this. A product of sum. Product means what? Multiply. What's a product of sums? Let's look at this expression. See this one here? Can you see it? I can't make it bigger. I can write it there. A product of sums. When I write this one, let's look at this one. This is what? Is that a product or sum? Sum. What about this one? That's also sum. And what are you going to do with the two answers when you get them? You're going to multiply the two answers. Because if you were to build that, if you were to go to the lab and build that, you have an OR gate for the first one. It has X, and you're going to go through a NOT gate. It has a Y through the other one. And the second gate is going to be what? 3 inputs, X, Y, and Z. And what do we do with the result of them? AND them together. Multiply them. So this is called the product of sums. So when the expression is written like this, called the product of sums, POS, product of sums. You adding there OR gates, and at the end you're going to AND them. You're going to multiply them. Product of sums. What about the other one? Sum of product. The other term. Let's look at sum of product. If I write this expression, f equals xy plus x bar yz plus x bar z. What is this term here? Product, right? That's an AND gate. What's this term here? Product. And this is product. And at the end, what do you want to do with these? You're going to sum them. This is called sum of product. SOP. Sum of product. So a lot of times you have mix and match problem, like we did one early today, and this one does not fit either one. Come back here. What was the problem I saw early? There's this one. And they might give you a problem like this, is write this as sum of product. It's not a sum of product. This piece alone here is what? These two is product of sums. This and this is what? Sum of product. You have both in one problem. How do we change this to make it look like this? Foil it, absolutely. Go with the foil. My first reaction to that problem when I saw it was to foil it. Now if I foil that, what do we have? xy plus, let's look at this. That's x bar times y, right? Then what? X bar times z bar plus what? zy plus z and z bar. Try again on z and z bar. That's a 0, right? Now let's look at these two, just these two alone. Don't worry about the rest of them. What can we do?
You can make it y.
Y.
Because x and x naught cancel.
X plus x naught, which is a 1, right? That's y. Plus x bar z bar plus yz. Can we simplify that more? How about these guys? Put them together. What do they have in common? 1 plus z. What's 1 plus z? Try again. 1. That's an OR gate. That's a 1. So this will be y plus x bar z bar. So when I take this problem, if they said write that as sum of product, this is my sum of product. There's my answer.
I mean, the second line was also sums of product.
Correct. I'm trying to simplify it.
This was a simple one.
Yep, because they're going to say minimum sum of product. They always want you to simplify, just like in algebra. They always want you to simplify completely. This is sum of product. Now, if they say product of sum, I'm in trouble. How would I change that to multiplications? I can't use that rule that I wrote early, a plus a bar b, because this is not the complement of that.
Is it the a plus bc?
I can do a plus bc. Do we have one for a plus bc? David?
A plus b, a plus b.
Yep. So we have a rule that says a plus bc. We can write that as a plus b times a plus c. So if I look at my answer now, here we go. Y plus x bar Z bar. When you try to compare them, A is Y, B is what? X bar, and C is what? Z bar. So I can take that answer and change that to A plus B. Y plus X bar times what? Y plus Z bar. And what do we have now? Product of sums. So write the answer of sum of product, we got it. Write the answer on product of sum, we got it. We use this rule. I applied that rule to this answer. I go, wait a minute, if I look at this, compare them, I should be able to write it like this. And there's my answer. So that's where these rules come in handy too. Notice here, I can't see that it's our book, I can't zoom in. We also have a couple of theorems called De Morgan's theorem for addition to these rules. And it says A plus B, and you want to do the complement of that. That's equal to A naught, B naught. And A and B, the complement of that is equal to A naught plus B naught. Boy, oh boy, do I use this in the lab. I use that in the lab all the time. Now in our book, the way they're going to write that in our book, because they're not going to put the bar over it, they write that A plus B, parentheses, and they go this one. And they write that AB, parentheses. That's how they write this one. But that's called De Morgan's theorem. What does that mean? Let's talk about this. Well, let's talk about these. Let's take the first one. We're going to be talking about two more gates. I said last class we are going to attempt to go to the lab this Thursday and build some of the stuff. The keyword, attempt to build. We'll see if everyone gets them to work. See how these gates work. So make sure you're here on time, because we might leave a little bit early. Like maybe around 10:30. So pack your stuff, let's go to the lab upstairs. I'll know how long it's going to take us. And we go there and we build what we're trying to build there. Show you what these gates look like. Now let me grab one of them. What this one is saying to us, if you have an OR gate like this, and you take the output and you decide to complement that, that will equal to an AND gate with both inputs complemented. Now instead of drawing these triangles here, a lot of times we draw these like this. And for the NOT, we put a little bubble. A circle here means complement. That's equal to an AND gate with both inputs complemented. That's the same thing. It means the same thing. But that's a new gate now. Anyone knows what that gate is called? That's a NOR gate. And we have them in the lab. That's a NOR gate. A NOR gate, it looks like this. If your inputs are A, B, and A NOR B. 0, 0, 0, 1, 1, 0, 1, 1. Just think of the NOR gate. It's an OR with the NOT. Now, a normal OR gate, what's 0 or 0? OR, what's 0 or 0? 0. Complement that, that becomes what? 1. What is 0 or 1? Complement that. What's 1 or 0? 1. Complement that. 0. What's 1 or 1? 1. Complement that. That's a 0. That's the truth table for that.
It's A nor B.
A nor B, yep. Now, watch this. I'm in the lab and I want a NOT gate. And I don't have a NOT gate. I go, you know what? This is what I need. I need you to take X and get X naught out of it. Sounds like snot, but X naught. Now I don't have a NOT gate. For some reason I lost a sleeve with all the NOT gates in it. Can I do this? Take a NOR gate and do this to it. Let's see what will happen. When X is 0, I'm going to have 0 or 0 here, right? 0 nor 0. What is 0 nor 0? 1. When X is 1, what's 1 nor 1? Looks like a NOT gate. So when I'm in the lab and I'm building and I'm using a NOT gate here, and I need a NOT gate here and an AND gate, why should I use another chip? I can use the same chip now by doing this. If there's some empty spots on it, to take that empty spot and create a NOT gate out of it for me. Now, I'll come back to this again. Let's look at the other one, the other De Morgan's theorem. Almost done for now. If I have A and B naught, it says that's equal to A naught plus B naught. Again, let's look at that. That's an AND gate. And put a NOT at the end of it. That's equal to an OR gate with both inputs complemented. Again, I can redraw that using just circles. This gate is known as what now? It's not an AND gate. It's not AND, which is NAND. It's the opposite to AND. It's the complement of AND. And we have tons of them. And here's a truth table for that. What is 0 and 0? And 0, complement that? 1. What is 0 and 1? Complement that? What is 1 and 0? Complement that. What is 1 and 1? Complement that. 0. Now again, watch this. I'm in the lab. I'm looking for a NOT gate. And I don't have it. I'll take an AND gate and tie both inputs together. Let's see what happens. When one of them is 0, that means both are zeros. When both are zeros, what's the result? 1. When both are 1, what's the result? 0. Let me just tease you a little bit before next class, set up what we're looking for. I'm in the lab.
Hey, can you put it back for a second? I was just getting thing written down. Okay, yeah, I'm good.
Anyone else? The last thing, I'm in the lab and I'm going to take the circuit I had before. I have X and I want a NOT gate. And this is Y. That was the circuit we had a few minutes early today. 4A, I think. We had Y, Z, and I have X, Y, and Z. And the result was OR together. That was 4A, the question today. And I said, you know what? I don't want to use AND and OR and all these gates. Just use one type of gate. I'm tired of all these different chips on the board. And maybe I can eliminate some of them. I want you to design this using only NAND gates only. Only NAND gates. Design using only NAND gates. Only. No OR gates, no NOT gates, no AND gates, only NAND gates. I do a lot of that stuff on the test and in the lab.
So we're going to learn how to do that next class?
Oh, I'm going to do it right now. Then we'll add more to it next time. Watch what I'm going to do. I'm going to double knot this. Double complement. When you double knot something, what does it do? Cancel each other out. So I didn't change the problem. Double knot this. Double knot this. What happens to all these gates now?
They become NAND.
They're NAND gates. Let me stay with them. Let me go back to De Morgan's theorem. What happens to an OR gate when all the inputs coming to it are complemented? That's equal to a what?
NAND.
NAND gate. So this is actually a NAND gate. See that? I used De Morgan's theorem. An OR gate with all the inputs coming to it are complemented is equivalent to a NAND gate. Now the NOT gate here, I don't want to use a NOT gate, so what do I do here? We said take a NAND gate and tie both pins together. Two of them here. And I might be able, instead of using 3 boards now, or 3 chips on that board, or and NOT, I might be able to squeeze that with 2 actually sets of chips because they all have NAND gates on them. I know I can use this for one chip has these on it. Notice these are 2 inputs, right? We said the chip has three inputs. There's 1, there's 2. I don't have a third one here. I can fix that for a NAND gate. Do I put 0 or 1? Here. I can put a 0, because when you complement that, that's what? A 1. So by taking 3 input, I can cover this, this, and this. Now, this, and that, all of them are what? 2 input? And I got another chip that has 4 2 input NAND gates on it. 4. So I can use this, one of the chip that has 4. I can use this, and this, another chip that has 3 input. And now instead of having 3 chips on the board, I shrunk it down to 2 chips. So that's where we're going to be playing with this Minterms, Maxterms, NOR, and NAND. Let me see for homework just for now. Sum of product of sum to play. Going back to the homework, last time I left